Okay, sections 5.1 and 5.2 are based on the rules of exponents, and we're just going to practice using these different rules, and then we're going to see how to apply them in the future sections. First, the first four rules we're going to look at real quick are the same rules as the rules from section 4.2, but we just need to reiterate them real quick. So first, if you are doing the product of powers, then what you're going to be looking at here is seeing that you have the same base A. And when you have the same base A, when we multiply two things with the same base, we need to add the exponents. So this base A gets carried over, and these exponents get added together. To show that it's true, though, take a look at this example right down here. X squared, y to the third, x to the seventh, y to the fifth. We'll just write it out. This is two x's, those are those. Y to the third, x to the seventh, y to the fifth. And then you see that there's two x's, and there's going to be 7 here, so that's 9 x's. There's 3 y's, and there's 5 y's, giving a total of 8 y's. So in the end, when you multiply, you're just really rearranging them. You're taking these 3 y's and tacking them on the end, and you're grouping these. So it's like you're thinking about the associative property, really. But again, the rule, based on this, what we see here is that when we multiply two things with the same base, we add the exponents. Rule number 2 is the zero exponent rule. Anything to the 0 power is indeed 1. A simple way to look at this, take a look at the conjecture. And it might be easier if you start with 2 to the third. Sometimes 2 squared is not enough to notice it. But every time you reduce by a power, you're noticing that this number halves, right? So we go from 3 to 2 to 1, it keeps halving. Well, if you go down to 0 now, you got to halve it again. Well, it's half of 2 is just 1. And this will work for any number. You can, instead of putting 2 as the base here, you could try 3, and it'll still work. 3 to the 0 comes out to be 1. And you'll divide by 3 every time you go down. Rule 3 is the power to a power. And the power to a power simply tells us that when you have a power to a power, you need to multiply those powers. That's why there's b times c. Different from the first rule where you added them. The easiest way to show this is to look at x to the third to the fourth. Well, that's really x to the third, x to the third, x to the third, x to the third. And from our earlier rule, we know we add these 4 together, that gives us a 12. But it's easier just to do 4 times 3, giving us 12. So we use our shortcut. And then finally, the fourth rule is the power of a product. And what we have to do here is realize that these are factors. When something is raised to a power, as long as they're factors, you can distribute it to both of the factors. If this was a plus b, that does not work. Only when it's a times b. So this c gets distributed to both. Easy way to look at this. Let's look at 4 times 2, that quantity cubed, and we'll look at it twice. First we'll look at it in a normal way, or a simpler way. Well, PEMDAS would tell us, look inside the parentheses first, so make this 8. 4 times 2 is 8, and then 8 cubed is 512. Or we could take a look and use this rule and say, well, I could distribute this 3 to both, making this 4 to the third, and this 2 to the third. 4 to the third is 64. 2 to the third is 8. 64 times 8 is indeed also 512, giving us the same answer. So it's no different. Okay, we can multiply first, then put this here, but this is just showing that this rule does indeed work. So when you have a power of a product, it's like you're distributing that power to both. Rule 5 is quotient of powers, and when we take a look at Rule 5, what we're going to see is that in this problem here, instead of product of powers, now we have quotient of powers. When we had product of powers, the rule was to add the exponents, and take a look. When it's quotient of powers, we subtract them. Let's prove that this is true real quick. If we have x to the 7th over x to the 4th, well, this is really x over x. And what we'll notice here is that these 4 x's cancel with these 4, leaving behind these 3 x's. Well, where does the 3 part come from? What's 7 minus 4? It's just 3. So when you apply the rule, just subtract the exponents. This is indeed x to the third. Now, in a moment, we're going to see what happens if, instead of having a numerator with a higher exponent, what if the denominator is a higher value? So what if this were now well, the rule says to subtract them, but this would give us a negative 4. Right? If we subtract them. But what does a negative exponent really mean? Well, it's easier to see if we write it out. Write this out over here. It's xx over, let me move the page over, x, 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 x. And what we'll notice is that these two cancel with these two, leaving behind a 1. And leaving behind 4 x's down here. So this becomes 1 over x to the 4th. Well, if I see this, these should be the same really, because I did the same problem just in a different manner. But this tells me that these are indeed equivalent. So what conjecture can we write? Let's take a look at the next rule. When you have a negative exponent, simply write it as 1 over the same value but with a positive exponent. And that was the rule that we just showed right there. Now let's take a look at where this rule here comes from. If we had x to the 4th over x to the 2nd all to the negative 3rd, we could start by distributing the negative 3rd, and we would get x to the negative 12 over x to the negative 6. And then at this point in time, we could realize that they're both negative, so we can switch them. Remember, this was in the numerator, it was really over 1. It moved to the denominator and became positive. So we could switch these and make them positive. Well, that's the same thing as if we just switched these to start. What if we switch these to start? We'd have x to the 2nd up top over x to the 4th in the bottom, all to the positive 3rd. And then when we square these, or then when we cube these, we get x to the 6th over x to the 12th. Right, distributing this 3 to both. Well, these are the same things. So this rule is indeed true. And when is it useful? It's useful when we have a negative on the outside, and you might possibly have some other values on the inside that are already positive. You don't want to mess around with them and make them negative and have to flip them. Just flip it and change the outer exponent that's being distributed to both the numerator and denominator. Alright, let's take a look at an example here. So let's imagine now we have x to the 3rd, y to the 2nd, all over x to the 4th, y to the negative 3, z to the negative 2. Alright, well with this example here, what we're going to notice is that we have some negative exponents. The first thing that we should do is move them immediately and just make them positive. So we start by rewriting everything that's positive. And then the things that were negative, we move them to the other location and we make them both positive. So this y to the 3rd comes from this one here, and this z to the 2nd comes from right here, up at the top. And now what we'll notice is that on the top, we have the y to the 2nd and the y to the 3rd, giving us y to the 5th up top. Z to the 2nd remains. Well, here we have 4 x's in the bottom and 3 up top. You could use the rule of 3 minus 4, and that would give you x to the negative 1, and then you have to move that down below. But instead, what I like to do is, I say to myself, well, it looks to me like there's 4 x's in the bottom and 3 up top. So these 3 are gone, and it cancels with 3 of these, leaving behind just the simple 1x, or that x that we would have had, even if we did it the other way. So this would be our solution with all positive exponents. Last rule is the power of a quotient, which we already looked at in the last part, because it's the same rule as the power of a product. And what we're seeing here is that if we have two things that are dividing into one another, we can distribute the power to each of them. So let's take a look at a complicated example now. So let's look at x to the 3rd, y to the 4th, z to the 2nd, over x to the negative 2. Let's make this a negative 4 up top. Y to the 2 and z all to the negative 3 power. There's a lot going on here. So the first thing I recommend is that we switch this negative 3 to a positive 3 and invert the fraction. So let's start by doing that. So I'm inverting the fraction, and I'm not changing anything. I'm not switching the negatives and positives, because I'm doing that and I'm switching the outer sign of the exponent. And I can do that from our rule from before. Then we take the 3, and it needs to be distributed to everything, because it gets distributed to the whole top, because the top, these are all factors, and these are all factors, and these whole things are an example of a quotient or divisors. So for this problem, we can distribute the 3 to everything now, giving us x to the negative 6, y to the 6, z to the 3rd, all over, x to the 9th, y to the negative 12th, z to the 6th. And now let's move our negative exponents around real quick. So in the numerator we end up with y to the 6th, z to the 3rd. I'm going to rewrite everything that's positive. X to the 9th, z to the 6th. And then I'm going to take into account these two because they're negatives. And I'm going to switch their locations. I'm going to put this y to the 12th up top. And I'm going to put this x to the 6th down below. So I'm going to move the locations and make them positive. And you could do this next step in your head. So I rewrote them, but we'll notice that there's really 15 of these, right? So this is really x to the 15th. For the y, there's really 18 of them. Right? 6 and 12, 18 of them. And then for the z, there's 3 up top. These 3 cancel with 3 of these, leaving behind z to the 3rd in the bottom. So that's z to the 3rd. And this would be our final answer for this problem. Your homework from this section is from 5.1 and 5.2, and then the review section from 3.3.